Alright, so in this video we're going to talk about graph modification algorithms. So these are kind of symmetric with the graph reductions, except these are white box. So here you're usually changing the pseudocode of a standard graph algorithm. For example, whatever for search, or maybe Dijkstra if you're computing the shortest paths. So the main benefit to graph reductions is because you're using the algorithm as a black box, it's usually very clear that your algorithm's correct. There's no weird dependencies on how the algorithm you're using works, and proving it's correct also is easier. So for white box algorithms and graph modification algorithms in general, the issue is now that you're changing the pseudocode, you not only have to have a good understanding of that pseudocode to make sure you don't break anything, and that's usually more difficult to prove things are correct, and you lose some of the power of abstraction there. But white box algorithms can oftentimes be faster than reductions, but reductions are always clearly correct. So there's, again, that trade-off between correctness and efficiency. Or correctness, complexity in the proof versus complexity in the algorithm. But sometimes they're necessary and useful, so let's consider some. So in this problem, this is a very simple mathematical problem. We're given some graph, we're given two nodes S and T, and in general, we're going to define this notion called incomparable. So two nodes are incomparable if S cannot reach T and T cannot reach S. So to get an idea of what that might look like, we're going to start with the first part, which says give an example of a graph where nothing's incomparable. So here's a really easy example. A, B, C, D. So here's nothing's incomparable because A can reach everything, B can reach C and D, C can reach D, and D is reached from everything. So for every node, so let's say C, either C can reach that node, so C reaches D, or the other nodes reach C. So C is not incomparable with any of those nodes. And you can use the same argument for the other ones. Okay, so there's an example graph where no pair is incomparable because either there's a path going to the right or a path coming from the left. So no pair is incomparable. So now let's consider a case where there are incomparable pairs. So one really easy example would be just something like this, where there's just a random node off in space. Obviously nothing can reach it, and it can't reach anything else, so these two nodes would be incomparable. But something like that's usually pretty rare, so we're asked to actually find a DAG that has exactly one source and exactly one sink with this property. So here, node V is a source and a sink, but this is not a DAG because there's a cycle on the left component. So if we want to make it a DAG, let's try something else. So we're going to have a source S, a sink T, and there's two other nodes, U and V. Now, since S is a source, things have to leave it. So maybe say edges go from S to U and S to V. And because T is a sink, only things can enter it. So just from what the problem asks us, immediately we get this picture. So then the only question is, do we have extra edges between U and V or not? So let's just go for the simplest example and let's figure out if this is good enough as is. So clearly S and T are comparable because S can reach T. And in fact, everything's comparable with S. So all nodes comparable with S because S can reach everything. In other words, there's a path from S to any other node. And similarly for T, everything can reach T. So S and T are out of question. So the only options here for incomparable nodes would be U and V. And I claim that actually they are incomparable. So why is this? Well, U can't reach V, obviously. And also, V can't reach U. The only option, if you're at V, would be to go to T and then stop. And if you're at U, your only option is to go to T and then stop. There's no way to get to the other one. So those two nodes are incomparable. And in a sense, you could think of them as they're in parallel. They're totally separate from each other. So there's some examples of what incomparable and comparable mean. So now the next part is, okay, so now that we have an idea of what these things mean, can we create a linear time algorithm to check whether a given DAG has an incomparable pair of nodes or not? So let's make a new page. So already we're told it's a DAG. So that should set off alarm bells that either we're going to be using DP or we're going to use some kind of topological sort. And that's just because DAGs typically are the only graphs with those special properties. So since the problem is telling us it's a DAG, it's probably for a good reason. So these are the two things we should think of. And since we're considering graph theory here, it's probably a topological sort. So let's just start with the topological sort. So let's say our DAG, if we sort the nodes, something like this. This is the topological ordering. Let me draw this edge like this. And then we have maybe say this edge, this, or not that one. And maybe this edge. So this is the topological order of our DAG G. And now let's think about if any of these nodes are comparable or not. So first of all, the very first one, let's call this V1, V2, V3, V4, V5. Let's assume that's the topological order. Then clearly V1 is comparable with everything because it can reach everything through some paths. Similarly, V2 is comparable with everything. But let's look at V3. So notice V3 can reach V5. It's reached by V1 and V2, but there's no way for V3 to get to V4 because this edge doesn't exist. And because it's a DAG and this is a topological order, if the immediate edge doesn't exist, there's no other way for V3 to reach V4. Because if there was a way for V3 to get to V4, it would require a cycle. So because V3 comes before V4 in the topological ordering, we know only path, well, we know if there was a path, did not use the edge V3 to V4, then it must it must follow a cycle. So pictorially, if there was this extra edge, it must be from V5 back to V4, which would cause a cycle. And that's, again, just because topological orders make sure all the edges go to the right. So if we didn't have an immediate edge from V3 to V4, the only other paths must have had an edge going left, back to V4. And similarly, there's no way for V4 to get to V3 without it somehow going backwards, either directly to V3 or backwards to something earlier that would then get to V3. But those edges can't exist. Okay, so what we've said here is there exists no pair, no incompatible pair, if and only if the edge Vi to Vi plus 1 exists in G for every I. And this is in topological order. So it's an if and only if, because if it's not there, then we just showed V3 and V4 are incompatible. Otherwise, if it was there, then obviously we always have a path. So for any Vi and Vj, where I is less than j, we always have the path Vi to Vi plus 1, and so on. We just always take the immediate edges till we eventually get to Vj. So, and similarly, if we just swapped it, so j is the earlier one, then j can reach I. So this is the key fact. Okay, so let me just emphasize this. So what's our algorithm? Our algorithm overall is just going to be compute in topological order of G, and then check edges Vi to Vi plus 1 exist. So the first part, that's O of V plus E. It's linear time to compute a topological order. And then to check all those edges, that's also V plus E. And this is just because we're touching every single vertex, so that's why the V is there. And then we're potentially touching every edge, because when we actually scan the adjacency list, the edge Vi to Vi plus 1 might be at the very end of each adjacency list. So we might have to scan through every edge just to get to that final edge. So because we always use the adjacency list representation, we have to get this extra E. So because this edge could be at the end of VI's adjacency list. So overall, it's O of V plus E's though. So always remember to consider how the adjacency list affects things. It usually doesn't really affect things much. It just added an extra E that we would have done anyway, but it would have been incorrect to say it was just O of V in this particular example. All right, so now how does this work for general graphs? So this was just for DAGs, and so we had the special topological sort power. But for a general graph, we can't topologically sort because there's cycles possibly. Well, here we can use that special trick from class. We can create the strongly connected component metagraph of G. And this is always a DAG. And then we can use the same alg as before on the strongly connected component graph of G. And we know that takes O of V plus E time to compute SCC of G using any of the algorithms from the textbook. And so overall, the algorithm is O of V plus E. So we have O of V plus E to compute the SCC graph, and then O of V plus E to compute on that graph. Since the strongly connected component graph is smaller than the original, doing linear time stuff on that graph will still be linear in the original graph. So that's great. We can compute this really fast, but is this even something we should be doing? Why would this work? So in general, the strongly connected component graph has different properties than the original graph. You're kind of abstracting away a lot of the complexity by doing this. So maybe we lose incomparable pairs by doing this. So why might it work? Well, for any node in the metagraph, so this is some meta node, capital, I'll call it capital VI. So any node in the metagraph is a strongly connected component, or a strong component. And so for any 2 U and V in VI, we know U can reach V, and we know V can reach U. So any 2 nodes in a strong component are comparable. In fact, they're very comparable. Not only does it satisfy one of the required relationships, it actually gets both. So for any 2 pairs of nodes in a strong component, we know for sure they're comparable, so we don't need to check for incomparability. So the only places where nodes could be incomparable is between different strong components. So in particular, this implies incomparability can only happen between nodes in different strong components. So if we know that, then it's equivalent to just check that 2 meta nodes are incomparable or not. It's exactly the same as checking individual nodes in pairs of strong components are comparable. So this implies the algorithm's correct. Okay, so there's an example where we'd use topological orderings and the strongly connected components graph to quickly compute something, some structural property about the given graph G. Now let's look at another example. So you might remember from the graph reduction video that we discussed the universe example and teleporting around. Our goal was really to find a max weight cycle, but we really didn't know how to do that. We can only create paths. So in this example, we're going to just see how we can actually find shortest cycles. And in particular, we're going to use our ability to solve shortest path problems to do this. So what's one easy observation? Well, consider any node S. Then any cycle has to look like this. and then an edge going back. So overall, every cycle involving S is an S to V path plus the edge V to S. So already what we could do is solve the single shortest path problem starting at S. So we're going to solve single source shortest paths. It's kind of a tongue twister on S. And then after we do that, this gives us a distance function, d of v, which is the shortest path length from S to V. In particular, this isn't a DAG or anything, so how do we do this? Well, we know the edge lengths are non-negative, and so the fastest algorithm we have for a general graph with non-negative edge lengths is Dijkstra's. So we're going to compute this with Dijkstra's algorithm, since weights are non-negative. And so that will take E log V time. So we can create this d of v function, and now to figure out the best cycle, we need to try all possible paths that then have an extra edge back to S. So the final answer, the shortest cycle containing S, let me call it SC of S. This is going to be the minimum over all nodes V. And specifically, let's say all nodes V that can reach S with a single edge of the distance from S to V, which we pre-computed using Dijkstra, plus the weight or length, so it's L in this problem, plus the length of the edge V to S. So we don't know which V is the last node on the cycle besides S. So what we do is we try them all. And so since any cycle from S to itself must be of the form a path, S to V plus the final edge, this will try all possible cycles. And so this is optimal. i.e., it's correct. Okay, so overall, what's the running time of this computation? Well, we have the O of E log V to run Dijkstra, and then we have an additional, we have to loop through all possible edges, and in particular, we'll also end up having to hit the nodes in the adjacency list to do that. So we have an additional O of V plus E, which is just O of E log V. Because typically we assume that the number of edges is very large in shortest path problems. So basically, what we did is we modified Dijkstra's algorithm to actually solve the cycle problem instead of just the shortest path problem. Which makes sense because cycles and paths aren't that different. And the key idea, essentially, was you could think of us as taking our graph and removing edges and then computing the shortest paths and then adding the edges back. Or you can just think of this as we computed the shortest path problem and we used the shortest path solution to solve the cycle problem. So in that sense, it's kind of more of a graph reduction than just graph modification. Depends on how you look at it. But that's how you do that. Okay, so we're going to do something similar in the third problem. Now, we're again going to think about Dijkstra, but we have exactly one edge has a negative weight. So here we do want to compute shortest paths, not cycles. But remember, Dijkstra's algorithm doesn't work efficiently when the graph has negative edge weights. It only works efficiently when every edge weight is non-negative. And in fact, if there's a negative edge weight, we could have a negative cycle, and so there's no solution at all. So we also have to check whether G has a negative length cycle. So we're going to use a similar idea from before. So let's take the edge U to V, which we know is the negative one. And let's say there was a negative length cycle. So this is some negative number. So a cycle from U to V that uses this edge has to include a path from V to U. So this is some V to U path. And so again, what we can do is run Dijkstra's algorithm on a new graph. So we're going to define G prime to be G, but without the edge U to V. We're just going to remove that edge from the graph. And then what we'll do is just run Dijkstra on G prime with the source being V. So that's where we're going to start. And so in particular, that will allow us to compute the shortest path from V to U. So this gives us D of U, the shortest path from V to U. And this quantity is well defined because in G prime, there are no negative cycles. Or actually, there's no negative edges at all, because we remove the only negative edge that exists in this graph. Okay, cool. So now that we have that, what's the length of the smallest cycle that uses the edge? Well, that's just going to be D of U plus U to V. This is the shortest cycle. Well, it's not even. It actually might not even be the shortest cycle, but it's the only contender for a negative length cycle. So this is the only possible negative length cycle. Using any other path from V to U would just have a bigger weight, and so we'd get a lesser chance of having total negative weight. So in particular, as long as this thing here is positive, there's no negative length cycle. But if it is negative, then that gives us a negative length cycle. So there exists a negative length cycle exactly when D of U plus the weight of U to V, I should have said weight there, is less than 0. So if in total that's less than 0, then this thing right here is a negative weight cycle. We can just keep going around and around the cycle and getting a lower and lower total cost. On the other hand, if that's positive, well then no other possible cycle using that edge could be negative. Okay? So overall, what we did was in O of E log V time, we ran Dijkstra's and just simply checked this condition. So overall, we get an O of E log V time to figure out if there is a negative length cycle. So now let's suppose there is no negative length cycle. Then what's the shortest path? So now let's assume no negative length cycle in G. What's the shortest path? Well, there's two options. So either the shortest path, which I'll say d of s to t. So it's going to be the minimum of two possibilities. It's either the distance in g prime of s to t. So in other words, it does not use edge, skips edge, u to v. Or it does use that edge, in which case the optimal path is the optimal path to u plus the length of the edge, u to v, and then plus the optimal path from v to t. And that's if we use u to v on the path. So those are our two options. The shortest path, this from S to T, is either the same shortest path as in the graph G prime, because it doesn't even need the edge u to v, or it's the shortest path to u plus the edge u to v plus the shortest path from v to t. And these are all in G prime. So we're kind of taking shortest paths in G prime and connecting them together with the edge to get the overall shortest paths. So that's the solution to the problem. So now what's the running time of this algorithm? Well, there's a couple of things we need to do. We compute Dijkstra 2 times, one on source S. That's how we get these quantities that have S first. And then we also have to compute it once on source V, which is how we get this quantity. And this makes sense because even to check for a negative length cycle, we had to run a shortest path starting at V to get to U. So overall, we run Dijkstra 2 times, and then we do this simple calculation, a minimum between 2 different options. So overall, that's just going to be E log V again. It's just 2 O of E log V's plus constant to do just a simple check. And that's our final running time. And again, correctness just comes from the fact that we either use edge UV or we don't. So pictorially, this is G prime. We have U and V. We find all the shortest paths. Find another shortest path. So once we have those 2 shortest paths, we can just connect it with the edge U to V. Or we can skip U to V entirely and get something else. So this one's D prime, ST, and this one is the other case. And that's it.